In order to start talking about limits and continuous functions in Calc 3, we need to at least briefly recap what we did in Calc 1. If you need more than the little recap we're going to do below, I would go to Paul's online notes. This particular link, I think, takes you to the limit page, and you're going to see there are many sections, probably hundreds of problems, many worked out if you need more than just a little teeny review. The first thing we do in Calc 1 is we define the limit. Now, graphically, by the way, what we usually do is just say it's the height of the hole. If we have to write down something, we're going to say that L is the limit if we can force the function values to be as close to that height as we want by choosing x values as close to a as we have to. That's pretty fancy. We don't really have that much option in Calc 1 to use that definition, that precisely, but the more calc you take, the more we're going to have to actually rely on that definition. After you do limits by looking for heights of holes, you usually talk about what it means for a function to be continuous. The definition that we come up with in Calc 1 is that f is continuous at x equals a if and only if the limit is equal to the function value there. The way we usually come up with that is we say, look, the limit is the height of the hole. F of a from algebra is just the height of the dot. And if it's continuous and the height of the dot is equal to the height of the hole, then the dot is filling the hole and the function has to be continuous there. Now, that's not the way we usually use it. The way we usually use it in Calc 1, we say, look, if we already know the function's continuous, you can evaluate the limit just by plugging in the value. That actually has a kind of cool thing, right? Is that combinations of continuous functions are continuous as long as they're defined. So even if it's a horrible looking function, as long as it's a combination of functions that we already know are continuous, if we can plug in the number there, that's going to give us the correct limit value. That actually starts up our procedure for finding a limit in Calc 1. The thing is, we always try plugging in first. Even if it's a horrible looking function, if we can plug it in, that limit's going to give us a correct answer. When people normally talk about doing limits in Calc 1, they're usually thinking of item B. If you can't plug in, you try to simplify the expression. So you expand and cancel, you factor and cancel, you fix the fractions, or you fix the square roots. If you can get to a point where you can plug in, that's going to be the right answer. Another thing that you use in Calc 1 is L'Hopital's rule. You try not to be too reliant on that because it doesn't actually explain anything. But if you're stuck, L'Hopital's rule is a way to go. Finally, there's lots of times, for example, usually end behaviors, so where there are any kinds of asymptotes. You try to analyze what's going on just to the left and just to the right of the asymptote, or you go way to the right and way to the left, and you're just trying to look at the function and try to draw a conclusion. That's usually sort of ad hoc in the sense of like, well, how can I rewrite this so I can draw a conclusion? But that's usually the second last thing we try. The last thing we try is what happens when the limit doesn't exist. Well, when the limit doesn't exist, the definition of that is the left-hand limit does not equal the right-hand limit. That's the definition, so we'd actually have to calculate the left-hand limit, calculate the right-hand limit, and show that it doesn't exist. In Calc 1, that doesn't happen a whole lot. In Calc 3, it happens a lot, and I would say about half of our limit-taking procedure is what we have to do to show a limit doesn't exist. That's our recap of limits from Calc 1.